Okay. I have 3 main subjects I teach in school. I teach chemistry. I was actually a chem major. So I love doing chemistry labs. And if you guys liked doing chemistry this last month and a half, you should take Chem 20 with me. And Chem 30. If you didn't like chemistry, that's fine. No hard feelings. That's kind of the part of Science 10 where one of my goals is to help figure out what you want to do. And it may not be chemistry. That's fine. Or maybe you have a passion like I do and you're like, this is kind of fun. And I want to learn more. I also teach physics. Forrester sometimes does as well, but I did it this last year. And physics, although not my major in university, is also one of the things I really like to do, which is why I like trying to find labs like racing Hot Wheels cars and shooting Nerf guns. It's fun. Okay. I think physics is a very practical, useful application in everyday life. And I hope that by the end of this unit, you guys would agree that physics is useful to someone somewhere. Like, for example, when you drive a car, the amount of physics that goes into a car, I don't even think I could think of everything. The physics behind what size tires should you use? What are those tires made of so that they stop on ice? Is there an airbag in your car? How does that keep you safe? What steel structured beams inside of the car will keep you safe? How do we make an engine work efficiently so that you don't burn too much gas? Does that make sense? That's just a car, let alone the rest of the world. So I think physics is, guys, can I get full attention? I feel like I'm getting half attention. I feel like physics is one of the most useful sciences. Okay. There's one problem with physics that people don't like. It's highly math-based. Today you don't need your calculators, but tomorrow and from then on, you're going to want an actual calculator. Not your cell phone, but you're going to want a real calculator. Physics is essentially applied math. And so if you like math, you'll probably be okay at physics. If math is not your strong suit, you probably won't like physics because pretty much everything in physics that we do involves calculations. Okay? So, by the way, after we do physics, we do biology. Biology is, for most students, actually probably their strength because it's a lot of memorization. And so if you're good at memorizing stuff, you'll probably be good at bio. I'm actually not the bio teacher, though. Lab usually does bio. So it's not my strength. I mean, I can teach bio, but I'm not nearly as, it's not my passion. My passions are chem and physics. So, that makes sense? Okay. Well, first we should then talk about what physics is. Do you guys remember at the very beginning of the chemistry unit, me talking about what the definition of chemistry was? Yeah. Anybody remember it still? What is chemistry? Study of how matter changes. Yes, good. Chemistry is about how matter changes. Okay. Well, to start off with, for physics, physics is the study of natural phenomena. That's really broad, though. Okay. So I want to maybe define it a little bit better. That's my next bullet point. If chemistry is about how matter changes, physics is about how energy and matter are related to each other. Quick reminder, what the heck is matter?
Anything that takes up space.
Okay, so anything that weighs something and anything that takes up space. It has to have a mass and a volume. Maybe a better definition of matter is stuff. This is a pen, it is matter. Okay. However, I'm going to throw it across the room. Pay attention. Okay. As it moved across the room, I gave that matter energy. Does that make sense? I gave it some energy as I threw it. That's physics. We talk about the stuff that we use in chemistry. Now, we're not going to change it, but we're going to give it energy. And energy can take a lot of different forms, hence that's today's lesson. I want to talk about all the different forms of energy that we talk about in physics. Okay. So, other things I have on the slide that are worth knowing. There's a huge correlation in physics between chemistry. A huge correlation in astronomy. Do you guys know much about astronomy? What is astronomy? Yeah, a study of like space and stars and things along those lines. A lot of early physicists were really astronomers, and they were trying to figure out how the Earth went around the sun, or how the moon went around the Earth. They were trying to figure out how all of these big pieces fit together. Okay. And like I said, huge correlation in math. In order to be good at physics, you got to be able to do basic math. Two more terms I want you guys to know. The terms are classical physics. Oh, I lost my highlighter. Classical physics and modern physics. In high school, we pretty much only teach classical physics. Classical physics is very old, I guess. Have you guys ever heard of Newton?
Yeah.
Isaac Newton. He's famous for like supposedly having an apple hit him on the head, and that he had this brilliant idea that gravity existed. Most of what we do in high school physics is classical physics, where we try to figure out how do things move, why do they move, where will they end up one day. Does that make sense? There's a huge amount of overlap with sports. Another reason I like physics. A baseball pitcher throwing the baseball, giving it energy. He puts rotation on the ball. His body undergoes a lot of torque and force. That's all physics-y type stuff. That's all classical physics. Does that make sense? Modern physics, New Age physics, there's some weird stuff about New Age physics. I already mentioned the idea of like teleportation, black holes, time travel. And that stuff, like, I barely understand it, to be honest. Because that's what, like, if you watch Big Bang Theory, that's what, like, Sheldon and Leonard, those are the sort of weird things they work on. Trans-Neptunian black holes. Like, I think they just make stuff up. But apparently that's what they're doing these days. So, okay, moving on. You know how I give you guys a history lesson in chemistry about a bunch of scientists? We're doing it again. History lesson. So, go way back when to, how did they put it in Big Bang Theory? It was a cool summer's evening in the Agora or market. We're talking way back when. They used to have some crazy theories about how the world worked. This is not true, by the way, but they used to believe that there were only 4 elements in the world: earth, air, fire, and water. You guys ever heard this before? Yeah, Aristotle used to believe this. That's the word you were looking for, right? Yeah. Aristotle used to believe that everything in the universe... Can I get full attention? He used to believe that everything was a combination of earth, fire, wind, or water. And when, like, say an object, it contains fire, so when you burn it, the fire gets to, like, escape. Keep in mind, like, these guys knew nothing about our universe. They didn't have microscopes. They didn't understand anything about atoms. We've actually mentioned this theory before in chemistry, I believe, the caloric theory.
Oh, is that for, like, what happens on Earth? Yeah.
Yeah. They had this idea of calories similar to phlogiston, where they thought that certain stuff had phlogiston and certain stuff didn't have this magical phlogiston substance. And they figured that, like, heat was a substance that all things had. They thought maybe there was like a liquid inside things, and that liquid inside it was heat, and that's what made it warm. Side note, do you guys know what heat actually is?
Energy.
It's a form of energy, but like at a molecular level, what's happening? Anybody know? Okay, Rebecca's got it. Can you say that louder?
The molecules are moving fast.
Yeah. Heat. Thank you, Gabe. I appreciate you. Okay. Heat. We actually now know what heat really is all molecules vibrate just a little bit. The more they vibrate, the hotter they are. Does that make sense? So at the time, though, they thought that heat was like a quality that everything possessed. So they thought that if you had hot chocolate that was really warm, they thought that somewhere mixed in that hot chocolate was this magical liquid caloric thing, and that that's what made it hot. They didn't realize that it was hot because the molecules were vibrating. Keep in mind, they didn't even know that molecules existed at this point yet. So, okay, here's the first guy I want you to know about. His name was Count Rumsford, and he had an idea. So if you guys can think back to like the 1780s, in my mind, I'm thinking of Pirates of the Caribbean. That's what I think of in my head. I don't know whether that was in the 1780s, but I'm thinking Johnny Depp and Keira Knightley and what's the other guy? Orlando Bloom. And they're all fighting each other with swords. And they're fighting on boats. And one of the best ways to take down a boat is you make a cannon. Does that make sense? That is like your best fighting tool in the 1780s. You use a cannon. How do you make a cannon? Well,
Iron.
to make a cannon, you take like a big piece of metal, like say iron, and you have to drill a hole in that big piece of metal. Because in that big piece of metal, you're going to shove a cannonball. Does that make sense? Well, it's not that hard to drill a hole in a big piece of metal. But you know what happens when you drill metal? It gets very hot. Like very, very hot, to the point that you're going to burn yourself. Does that make sense? And so here's what he was looking at. He said a hole was bored to make a cannon, and everything started getting hot.
Yeah.
And Rumsford was kind of questioning, why? Why is it getting hot? Where is this magic caloric coming from? Because I'm not adding something new. Here was a cold piece of metal. Here was a cold drill. And as I drilled the piece of metal, all of a sudden, caloric magically just showed up. And he started to question why. Does that make sense?
Caloric stuff that comes up like the
Well,
energy.
caloric is what they believed at the time, but it's not actually true. Does that make sense? And so here's what he then concluded. He concluded that there must have been some sort of mechanical energy getting converted into heat. As a person turned the crank to bore the hole in the cannon, their energy, the energy of a person, was getting converted into a different form of energy, being heat. And this is one of the first known people that we know of that actually had like energy ideas. Second scientist. His name was James Joule. You might have even heard this name before because we've named, in honor of him, we've named energy as joules after him. Yeah.
That's James Joule.
Okay. Here was his experiment.
Your real name James Joule. Yeah.
I don't suppose I could keep teaching. Thanks. Okay. Here was his experiment. Okay. He was trying to figure out how energy and heat were related. And so at this point here, we had figured out gravity. What he did is he attached a weight right here to a pulley system. You guys see how there's like a pulley right here? As the weight would fall, it was going to cause this little thing to spin. And as this thing right here spun, whatever the proper word is, as this thing was spinning, it was going to twirl, right? What's going to happen to the temperature of the water? It's going to go up. It's going to get slightly hotter. Now, I mean, I'm not talking it's going to boil the water, but does that make intuitive sense to everybody that, like, as the weight falls, this thing spins, the water heats up? He was one of the first people who kind of came up with the idea that energy created heat. Does anybody know what sort of energy, though, we call it when a weight falls?
Gravity.
Yeah, gravitational energy, yeah. Right here I have a pen. This thing has energy. If I let it go, it'll fall. That is a form of energy. Okay. What's happening is gravitational energy is turning into a form of energy called kinetic energy. You guys ever heard that word?
That's the word I was looking for.
And that kinetic energy was going to then stir the water. And basically what Joule was able to do is he was able to relate temperature to how much work was done on the water. Like this water in the beaker. This was in 1840. We're talking only 200 years ago. And at that point, scientists still did not fully understand things that you guys take for granted today, like understanding how heat works. They didn't get it at that point. They just knew that stuff got hot. They didn't know why. Okay. Here's some current theories of energy. Energy is sometimes referred to as having mental or physical stamina in the non-science world. Like, for example, if I give you an energy drink and you're like, ooh, buzzing, you might say you have a lot of energy. That's not really the same thing, though. Does that make sense? Energy from a physics point of view is actually a very hard thing to answer. We actually don't have a definition of energy. That may sound crazy. But like if I asked you define energy, there really isn't one definition that scientists universally agree upon. Because energy is just such a broad term. Okay. Here's what we do know, though. Two things. Energy is needed to do work. If you want to accomplish something, you need energy. Let me give you an example. I would like these light bulbs to turn on. That's going to accomplish some sort of task. That's like doing work. Does that make sense? Why do these light bulbs turn on? It's not magic. How do they turn on? Well, I flicked on a switch. Okay. But like, that just completed a circuit. Where is like the root source of the energy that causes the light bulbs to turn on? Electricity. Where's that electricity come from? A generator, maybe. How about in southern Alberta, we have those windmills out in the fields? Does that make sense? Well, in order for this work to be done, there must have been some sort of energy coming, the energy being the wind that causes the turbines to spin. So wind energy causes turbines to spin. Turbine spins, makes generators work. Generators create electricity. Electricity happens in light bulbs. Now work is done. Does that make sense? Scientists are able to determine that work and energy, they always seem to go together. If you want to accomplish a task, you need energy of some type. If I want to, if I want to paddle a boat, I need to do some physical work using my energy. Or I go find a motor. And then how does the motor work? Well, it spins because an engine undergoes like gas will combust. And then that's another form of energy, the energy that we find in like gasoline products. My second point here, energy comes in many different forms. This is the key word right here. Energy gets transformed very easily. Sometimes energy is stored, sometimes it's moving. For example, when I was really little, I would take elastic bands and I would shoot them at my sister. Anyone ever done that before?
Oh yeah.
Yeah.
Never in my life.
Never in your life. Well, what's happening in that transformation there? Well, I as a person am using some of my energy to find an elastic band and pull it back. Then, as I pull it like this, is anything actually occurring?
Nothing yet.
Well, we would say there's potential energy at that point.
What's that stuff called? Genomic? Or
I don't know what you're looking for.
never mind.
Okay.
Something.
As you pull the elastic back, there's potential energy waiting there in the form of like elastic energy. Then as I let the elastic go, all of a sudden the energy has been converted to a form of energy called kinetic energy, a type of motion energy. Does that make sense? And then eventually the elastic hits my sister and she says, "Ow, stop that, Chris."
Stop it.
Does that make sense? Energy is very easy to transform between different types. If you like sports examples, a baseball pitcher like Roberto Osuna, he was really good the other day there.
He killed it.
Yeah, 4 strikeouts out of 5 guys. Anyways, I digress.
That's awesome.
He uses his own energy that he got from probably eating some food beforehand, right? And he winds up, he throws the ball. The ball now has kinetic energy of motion. Now, Osuna actually struck the guy out, but let's say a guy hits the ball. Well, now the energy of the ball has transferred from the ball to the guy's bat, and he's going to feel a vibration on his hands as he hits the ball. Does that make sense? There's energy being transferred. And if he makes good contact, hopefully that ball will go a long ways. Well, not if it's not against the Blue Jays, obviously.
No.
Does that make sense?
He's too good.
Okay. I hope I'm making my point clear here. Scientists do not know what energy really is. It's hard to define energy. But we know what it does. We know that it transforms all the time. And we know this. We know that it's always involved in accomplishing a task, doing some sort of work. Does that make sense? Okay. So the next few slides, I'm going to talk about all the different forms of energy that we typically would consider. Okay. By the way, energy is based on the Greek word energos, meaning active. Energy is supposed to refer to something that's happening. But that's actually a poor choice. Because right here I'm holding this pen. Is anything actually happening? It has the capacity to happen later if I let go. So there are some forms of energy that are passive energy. Sometimes we use the word potential energy, where this is actually gravitational potential. It will happen later. Does that make sense? So although energy means active and motion, there are passive forms as well. So here's some forms of energy I want you to know about. Form 1, chemical energy. For example, when you make a fire, where is the energy from the fire coming from? Well, it's coming from chemicals. Technically, the wood that you're burning, it is releasing energy from its bonds. Energy in the cellulose molecules is released due to bonds. Certain things have a lot of energy in their bonds. For example, dynamite. for how little dynamite is, there is a lot of energy in its bonds. And if you break those bonds, it blows up really big. Okay. This pen right here, it has some energy in its bonds, but it probably won't light on fire quite as well. It'll just melt. Does that make sense? So certain things, their bonds just have more energy than others. And that means that it can blow up better. Here's the thing though. Chemical energy is a potential energy. If I have a stick of dynamite, is it doing anything at that point if I just hold it in my hand?
No.
Okay. It has the capacity to release a lot of heat and a lot of light and a lot of damage, I guess, as well. Does that make sense? But it's actually a passive form of energy, chemical energy. It's not reacting yet, but it will one day. Makes sense? When you guys eat food, that's a form of chemical energy. You are giving your body chemical energy stored up in your muscles in like sugar storage, in fat storage, so that one day when you need to actually use that, your body is able to. Does that make sense? If you were to stop eating, you would run out of energy. Second form of energy, electrical energy and magnetic energy. They're actually interrelated. Okay. Most of this, you guys might even just intuitively know. If I have a magnet and something that is magnetic, I can get those two things to like stick together. Hey, girls. Does that make sense? That's a form of energy. Magnets are actually a form of energy where you can do work using magnets. Okay. We actually discovered that you can actually use an electric current to make a magnet, or you can actually use a moving magnet to create electricity. It's kind of a tricky concept. We actually covered it in Physics 30, but you guys probably at least at the very least know that there's electrical energy, right? That's a form of energy. Electricity is a form of energy. It's actually very closely related then to magnets. Okay. Okay, other forms of energy. Nuclear energy and solar energy. Curtis, I hardwired that into the computer. It's the only way I can get it to work.
Yeah, these ports aren't live.
That probably explains it. Although the back port right there is where it stopped working as well. So anyways.
I have a question. What's out
Yeah.
of there?
What was that?
Yeah, like,
Oh, these are just some pictures of, like, you guys know electricity, right? When you just
Yeah.
plug something into the wall.
and like, is that how it looks inside of these things?
No,
Oh.
no. Do I have enough time to do it today?
Yeah.
Yeah, I do. Okay. Give me a second here. I'm going to do a demo. I do this on my Physics 30 kids. But
I guess we'll do it today. Just need a second.
okay. Do you think everybody would be able to? I've only got one set. You guys maybe come closer over so you can see this. I'm gonna do a couple of demos here. Okay. Does anyone know what this device is?
The ammeter.
Yeah, no P in the word. It's actually an ammeter. But it measures amps. But like the word doesn't have a P. But you're right. It's an ammeter. Basically, this is a device that measures electricity. Okay. And so if there is electricity running through this circuit, what should happen is this little line here will move up. Does that make sense? If I had, I don't know, if I had strong enough battery and I attached it to it, you should hopefully see the little thing move. Does that make sense? What someone really smart once discovered is that magnets and electricity actually go together. This, by the way, is just a whole bunch of little pieces of magnetic iron inside there. And if I like use a good enough magnet, really not a good enough magnet.
Whoa. No, you shut this side?
No, it's not doing anything. The magnet's not strong enough to do anything. You guys know how magnets work, though, right? Okay. If the magnet is good enough, it should actually stick. Magnet. Okay. Here's what a really smart guy once figured out though. If I take a moving there we go. Okay. All I'm doing is taking a magnet and a coil of wire. You guys see how the needle is sitting right there? Watch this. I made electricity. Yeah, I know that maybe seems kind of weird, but there are properties about electricity and magnets that go together that honestly I can't really explain until grade 12. That's when we cover it. But generators are actually made using magnets and coils of wire. And as you move magnets and coils of wire together, it actually causes electricity to happen. You guys ever hear of AC versus DC? AC is called alternating current. To make alternating current, that's what I'm doing right here. I'm making alternating current because it's going this way, that way, this way. If you guys can see how the little wire is moving back and forth. I actually did this with you doing Science 24, didn't I? Yeah. So, does that make sense at all? Long story short, this is a form of energy. I did work by making this magnet and this coil of wire go together. Oh, I lost the wire, that's why. And there was actually electricity running through this thing. If you care to know more, maybe ask me later. I'm kind of giving you like the 2-second version. It's quiet. Okay, moving on. Other forms of energy you guys probably have heard of before. Let's start with solar energy. Where does solar energy come from? The sun. You guys probably knew that, right? What you maybe didn't know is that the sun is actually a nuclear reactor. So like when I think nuclear reactor myself, I always think of The Simpsons. You know, like that big nuclear reactor that Homer works at. Well, technically that's actually what's happening inside the sun. The sun is undergoing what's called a nuclear reaction, where, you guys remember how we discovered there's nuclei of different atoms? If you take different atoms' nuclei, and you force them together, it actually releases a lot of energy. Forcing two things together is known as fusion. You ever heard that before? Okay. That's what the sun does. The sun undergoes a fusion reaction in which, in the sun, it's a hydrogen. Ooh, that's not a pen. A hydrogen nucleus plus another hydrogen nucleus. They actually merge together, and they form helium. And in doing so, it releases a ton of energy. That's called a fusion reaction. The other type of nuclear energy is when you split a nucleus, and that's known as fission. It's where you take a single nucleus and you rip it apart.
What about like kill it?
Well, usually fission reactions give off a lot of nuclear radiation as well, and so you got to be careful, like hide behind a big lead barrier because you could end up getting radiation poisoning from it. But this is another source of energy then, nuclear energy. We're not talking chemical energy. We're talking the actual nuclei of atoms, either getting forced together or ripped apart. Okay. And then here's another list of other forms of energy I'd like you to know. I'm not going into nearly as much detail, but maybe some of these make sense. What's thermal energy then going to be? Yeah, heat. Yeah. We already talked about chemical energy a little bit. That's energy formed in bonds of chemicals. Electrical energy is like electricity. Radiant. Yeah, like a kind of like electromagnetic radiation. There's energy there. For example, if you guys have like a Wi-Fi router in your house, it actually produces radio waves, or well, it doesn't produce radio waves, but it produces waves that your cell phone picks up on. We talked about nuclear energy a bit, magnetic energy a bit, elastic energy. Well, that's like when something is stretched, like when I flick the elastic at my sister. Or basketballs actually involve elastic energy. Yeah, why doesn't a basketball bounce back up again? It compresses a little bit, and it squishes in, and then it bounces back out again. For anyone who's watched a hockey game, you see like those hockey sticks where they have flex in the hockey stick, where the guy's got the hockey stick like bent. You know what I'm talking about for that?
Yeah.
That's elastic energy, where it's just waiting to flex, and then it's going to snap the puck at the net and hopefully score a goal, right? So that's elastic energy. There's also energy in the form of sound. I'm going to skip this one for a second here. Luminous energy. Good light, yeah. Another word we'd use. Luminous light. There was once a very famous guy, you might have heard of him. Albert Einstein? He was a minor scientist. He had a very famous theory that you may have heard of as well. I'm being silly. You guys have heard of E equals MC squared at some point?
Oh yeah.
It's like Einstein's famous formula. Einstein actually discovered that mass actually contains energy as well. The formula for E equals MC squared, E is energy and M is mass. And we actually do that also in Physics 30 at some point. I skipped one though, I should come back to that. Mechanical energy. Mechanical energy is an overall term that just describes all energy. Like, we're not talking energy in machines or energy in something mechanical. Mechanical energy is a term that we use to describe all of the energy that exists that's kind of happening. Let me give you an example. Let's say that you go sit in front of a fire. Is there energy happening when you sit in front of a fire?
Yep.
Okay, let's talk through what's happening. What is the source of that energy? Where's it coming from? The wood. That's chemical energy. So that's one form of energy that's happening. As you burn that wood, that chemical energy is getting turned into light, luminous energy, heat, probably, thermal, probably some sound, like, because you can hear a fire crackling. Does that make sense? Well, collectively, all of those forms of energy, we would call that mechanical energy. Does that make sense? So mechanical energy just refers to, in general, all of the different types that are happening. Okay, that's it. That's my lesson. So here's what I need you guys to know. Two scientists. Count Rumsford. He was the guy who was trying to figure out why does a cannon get hot when you make a hole in the cannon? You have a cold piece of metal, you have a cold tool. Why does it get hot? That seemed odd to him. Doesn't seem odd to you guys probably, but to him that was strange. Another scientist afterwards worked more on it. James Joule, had the idea of let's drop a weight. The weight is going to cause something to spin, and it's going to heat up the water in a beaker. He was trying to figure out how gravity energy could actually cause the spinning of water to create heat energy. And then the last thing I need you guys to know is just know all of these different forms of energy that exist. Because there's a lot. And energy is a really hard term to narrow down. So what we do know about energy is that you need energy to do work. If you want to accomplish something, you better have some energy. And then secondly, energy changes all the time. It changes from elastic to kinetic. I didn't actually even put kinetic on this list. Kinetic energy is like an energy of motion. I should write that down here. Kinetic energy refers to something that is like moving. So when I throw a baseball, I give it kinetic energy. Does that make sense? Alright, cool. That's our lesson. Here's what I'd recommend you guys do with the last little bit of time. If you haven't finished anything from chemistry, can I get that ASAP? If you're going to hand something in late, that's fine. I don't have a problem with taking it in late, but make sure you do a darn good job of it, because you're going to count it. I've already talked with a few people just about the idea that if you want to improve your marks, maybe take back your assignment from me and make sure that it's fantastic, rather than handing me something in just for the sake of handing it in. I really want to change your mindset. Don't just hand me an assignment because I tell you it's due. Because if it's going to be a piece of crap, how does that help you? Does that make sense? So only have me mark something if it's going to be good quality. So if that means it's late, I don't mind. I would rather you hand me a great assignment that is late than hand me something that's garbage. But that way you said you handed it in on time. Does that make sense? Okay. One more thought then. You guys, if you'd also want to get a head start, on my website, I already have a few of the first things you could start working on. If you go to the Science 10, the notes. If you'd like to, you can print off the assignment for physics. You won't be able to answer every single question, obviously, but I would really strongly recommend do what you did last unit if you just do a little bit every day. Like, for example, the first question, describe some contributions that Count Rumford and James Joule made to our understanding of heat and energy. You can probably talk about that now. Or the second question, state and describe 5 different forms of energy. Give examples. Like the rest, do it a little every day. Does that make sense? So maybe what I'll do is I'll leave this up on the board. That way, if you want to try the first 2 questions, you can. The other thing, though, that you could print off is the video assignment. You probably can't answer the questions until we watch the video, but at least you can kind of look at them a little bit and see what it's going to be about. Because we're watching this video, I think it was next week, or the following week, Thursday. So, anyways, I'm done. Any questions? Okay. Oh, one last thought. Next week, Friday, can you guys make sure you're here a little closer to 11:08? It wasn't really a big deal, but it can be. So try to make sure you're here a little closer on time for Fridays. Okay, cool. I'm done. Scatter. Do what you need to do.